Thank you, Dara,
Great.
for the invitation.
Perfect. Okay, so welcome everybody. Thanks for attending our Power Electronics webinar for today. This is sort of this lunch and learn webinars that we started, and we want to introduce new technologies to the South African and African area. So myself, I'm Laura Van Niekerk. I work for Kievensoft, and we're the sole suppliers of Ansys simulation software in Southern Africa. And I've got my colleague Evan, who's going to do the presentation on power electronics for you today. So we are both based in the Stellenbosch region, working for Kievensoft. So there's two offices. One is in Irene, one is in Stellenbosch. So we're here to support you guys locally and also up into Africa. So as I said, we're going to focus on the power electronics webinar for today, and I'll hand over to Evan to do a quick introduction, and then we can start with the webinar. Okay.
Cool. Thank you, Laura. Yeah, so as Laura said, my name is Evan Smuts. I'm an application engineer at Kievensoft. So my part or role is to do the technical support for the region. I have a bit more of a mechanical background, but these days everything's going towards electronics, so kind of venturing more and more into that region. Cool. Let me just share my screen. Laura's the screen coming through?
Yeah, we can see it.
Cool. Okay, so we're here to look at various solutions that Ansys can offer for power electronics sector. As you'll see, there's quite a few options and different applications where we can be of some help. So we'll start off with a quick overview of Kievensoft, who we are, for those who don't know, as well as then looking at an overview of Ansys as well. Then we'll have a look at the sort of overview and why we want to simulate with power electronics and with simulation, and then have a look at some different applications from there. Yeah, so as Laura said, we've given us a bit of intro to Kievensoft. We've been around for 25 years now, and we have operations in both Pretoria and Stellenbosch region to sort of service the whole South Africa. But obviously, as time's going on, we are working more and more in the rest of the African continent as well, as you can kind of see by that graphic. Sort of the territory in blue is kind of the area where we're servicing and trying to expand our reach. And as Kievensoft, we are not Ansys ourselves, but we are the certified resellers of Ansys. So we offer all the pre-sales support and training, as well as all the after-sales technical support as well. We do also sell the product CF Turbo, but that's more on the turbo machinery side of things. And then with Kievensoft, we also offer design and simulation consulting services for those who maybe don't actually want to buy the package outright or straight away, and they first want to just use it on one or two projects here and there. So that's kind of us as Kievensoft, looking at Ansys and who they are. Ansys is considered the #1 engineering simulation software provider in the world. The idea is that they focus purely on simulation software across the spectrum for many different types of physics, and that's where they kind of offer their strength. It's kind of their core focus, and in that sense, they can offer a number of different solutions for any type of simulation challenge. And traditionally, they've been known as or seen as just providing single solutions for single physics, so like your structural analysis, fluids with CFD, even electronics. But over time, it's about integrating all these different physics together into a single solution. So we talk about multi-physics approaches where we combine the different physics together, and then also taking a bit of a higher level look in terms of actual systems simulating, so providing either just a system simulation or even a digital twin where we connect our simulation to the actual real world asset. And then combining that also with even the control software and other safety concerns as well. So it's about the Ansys offering is not just looking at a particular type of analysis, but how can we also bring all these different analyses together into a much more detailed picture of our problem that we're trying to understand. And as part of this kind of offering, it's, again, typically simulation is seen as something where we've designed a product and now we just need to check it before we make it. But that kind of comes very much at the end of the design cycle. And if there's any issues that we need to address, it gets a bit late in the process to do that. And there's a whole time and cost ramifications from that. So Ansys is really about bringing in simulation at every stage of the product's life cycle. So right from the conceptual phase, coming up with different designs, getting rid of the bad designs quickly and focusing on the good ones, right up until even in the actual operation of the product. Okay, I talked earlier about digital twins. So that's where we can actually monitor the operation of the product and how does it performing relative to its design prediction. And maybe we can get some insights into the operation of the product and the design of the product by comparing those two sides of the picture. So simulation is not just about looking at one snapshot of the design phase. It can really help us at kind of every level along the process. And so our goal is to kind of offer lots of solutions at each stage of this process. And then through this over the years, Ansys has built quite a large range of different products. As you can see here, this is quite an extensive list. It's not the total list. There's been a few more added since this list has been put together. But the idea is that we cover quite a large range of different physics and different applications within each physics region or discipline. And what we're going to focus on today is power electronics, but we kind of bring in solutions from different areas, from the electronic side, from the structural side, even the coding software side as well. So we'll look at some of these different solutions, what we have to offer, and where they fit into the workflow. So firstly, why simulation? I guess that's always the big question. Why do we need to simulate something? So when we get to something like power electronics or a subject like power electronics, we find that, there's kind of main pillars of what we're trying to do. Okay, we're always trying to make our products better, kind of consider these three main pillars: performance of the product, safety and reliability, as well as the overall cost of the product. Okay, we're trying to kind of find the balance between all of these. We can get a very good performing product that's very safe, but maybe it costs too much to be viable. So we need to always kind of consider the balance between these items. And when it comes to power electronics, there's many different areas that we need to many challenges that we need to be able to understand. So, as the components are getting smaller and smaller and frequencies, for example, are getting faster and faster, it's putting a lot more strain on the performance of our requirements of the performance for the device. We'll also reach problems with over voltages, breakdown of the materials that we're using. This could be, from the EM side or come from a thermal aspect as well. Are we overheating the components? And then also, how does this component fit into an entire system? Is it going to perform as part of a larger power supply sort of system? And then also other challenges like EMI, EMC as well come up as we are pushing the limits of our products. And then obviously lifetime. We do want our products to last longer, be more reliable, and therefore add more value to our customer. So as we try and achieve, or the reason we want to use simulation is to try and better understand all of these different topics and how we can address them faster as well as more efficiently. Okay, so these are some sort of numbers to kind of throw around how simulation can help you. Yeah, these items here are some case studies that are available on the Ansys website if you want to go and have a look at them. And they talk about things like increasing the speed or turnaround time of our simulation. How can we get answers of a newer design much more quickly and therefore make better decisions in a shorter time? How can we reduce our design cycle? Often design is a very iterative process, but if we can sort of understand each iteration better, we can do less design iterations and therefore get our product to market faster. And obviously saving time invariably saves money. So that's part of it, but also just also saving on materials and failures of prototypes that had some issues with it that we didn't understand. So this is where simulation can come in, is to kind of help us get answers faster, but also understand them better, so that we can get to our final goal in shorter iterations. And then these are two more case studies that we have with clients around the world working with Ansys. So on the left, we are working with what used to be Fairchild Semiconductor. They're now called On Semiconductor. And it's all about how we can use reduced order models to reduce development time for electronic components, in this case specifically for electric vehicles, and how we use different products within the chain to understand the overall performance much more quickly and get to a better design much more quickly. On the right there, again, example looking more at sort of the electronic controls for HVAC components. So this is now working in collaboration with Danfoss to just, again, understand their products better, to make them more efficient. Particularly energy efficiency is a big question these days. And then obviously more reliable as well. Okay, so this is some use cases where simulation has already helped some existing clients. Right, then understanding power electronics, the sort of the workflow and what we're trying to do with this, because power electronics is quite a big topic. There's a lot of different aspects that need to come into play, and these days the demands of power supplies are getting more and more. So we're having to push the limits of design and materials as well. And this is where Ansys is coming in, just to bring sort of a number of solutions. We don't talk about software packages, we talk about solutions to your challenges and how we can make this design process faster and smoother. Okay, so always as we're going through this presentation, always just kind of keep in the back of your mind what are the kind of the cost and time savings that can come in by applying simulation into the design process. All right, so as with many of the challenges today, power electronics is a very multidisciplinary field. Here we're trying to sort of integrate and combine and collaborate between different teams working in very different disciplines with different types of physics, real physics that we need to consider, and how do we bring this all into a final design that's going to work as we intend. Okay, so we've got the electrical team that's actually designing the function of the components. We've got the mechanical team that are looking at the reliability and the physical structure of everything. And then the software team as well, coming in from their control, because some of the more complex systems need software control to keep them always optimized in their operation. And then obviously the electromagnetic and thermal team sort of bring this together into understanding the performance of the team and how we can get better performance out of the components. Okay. So looking at all these different disciplines and then looking at all these different challenges that we have to meet to design these type of components, there is quite a comprehensive list here, looking at right from system design to the actual magnetic components, to looking at some of the parasitic processes from EMI, EMC, thermal degradation, all of that kind of stuff. And how do we kind of look at each of these different challenges and how can we so solve them. Okay, because they're in some ways related, but also very different in how we go about tackling them. So as we now delve into these topics a little bit more in depth, and we can see kind of what Ansys has to offer for these. So first up is looking at system level modeling, where we'll talk about ROMs or reduced order models quite a lot. So when we have our large system, or when we start off with our design, often we have to consider it as part of an entire system. Okay, it's not, we don't always dive down straight to the components. We first need to look at the system. How does the system operate and what are the system requirements? And often that puts various constraints on our different components. And as we're pushing for higher power densities, increased efficiency, and then having to consider all the EMI and thermal issues that come with that, you know, we need to sort of get a general understanding of the bigger system and how it operates. And sometimes that's very difficult to do if we delve into a very detailed physics analysis of a particular component. If we try and apply that style of problem solving to the whole system, it will take forever to get answers. And so this is where we build a system model where we kind of integrate mixture of very basic components, in this case, sort of standard electronic components that are just very simply represented. And then we can, as we develop the system, we can then integrate actual components within that system that have a lot more detail right down to, you know, all the nuts and bolts, as it were. So this is where we talk about system design and multi-scale modeling, and how do we kind of combine all these different levels of detail together. Okay, and obviously a system level design, we should be able to get answers fairly quickly, and that's kind of the goal behind this. So we just kind of iterate or illustrate here how we can build our system models from the very simplistic components, so whether it just be inductor, resistor, or something like that, as a very simple circuit element, to looking at a slightly more detailed design through using various analytical models and empirical models. We can start designing specific components. In this case, P expert for transformer design. We can look at the actual component itself, but using much more simplistic modeling approach, so we can get a very decent answer very, very quickly. And then we obviously can go to the full 3D analysis, where we actually build the component in 3 dimensions, assign all the material properties, and then we can calculate the full field values from that. Okay, so depending on where we are in the system workflow, we can look at different levels of accuracy or fidelity within that. Okay, or sometimes I think of it as resolution. You know, what is the resolution of the answer that we want to see? And what we have on offer, a lot of the products that we talk about today, they are not linked to a specific design. Okay, we can go, you know, it's the software is very generic, very open-ended. It's up to you to create your design within the system and define how it operates, and then we can simulate it from there. Okay, so in this sense, we're not locked into a particular type of product or particular type of application. It's really up to us and what level of detail we want to include. So we can do anything from the tiniest of sensors up into, you know, the actual power supply in terms of bus bars and cables, and even at the full machines and actuators and motors and things that actually is what our final goal at the end of the day. And then, for example, if we take a bus bar and we do a 3D analysis within, for example, Q3D, so this is looking at the actual 3D design, looking at the currents and voltages in the system, maybe even linking that with a few sort of state space models for circuit components up and downstream. we can then study the electromagnetic behavior of that bus bar. And then once we've got that detail, we can bring that into our circuit analysis to look at how it functions within a bigger circuit system. Okay, so the idea behind this is we represent that detailed component as a reduced order model or a ROM that then cuts out or allows us to much more simply represent that model much more simply. So we're not having to solve a full 3D field model every time. It's just a simple lookup table or analytical relationship that governs the behavior. So we take some inputs, calculate it, and it will give us appropriate outputs for that particular model. Okay, and so we can use that model within a larger system, but without actually having to wait hours and days for an answer. It can give us an answer within seconds. So that way we can test our system under real-world conditions, make a few changes as we need to, and get a sense of whether our system will work appropriately or not. And then if it's not working, we can then take a deeper dive back into, say, for example, the 3D model, and maybe make some changes to our design and see how that influences our global performance. So then looking at specifically at the components that we want to work at. So this is where we start doing a bit of a deeper dive into each component. Again, we can have a number of tools available to us, depending on the type of application we're looking at. So we can look at anything from ductors, transformers, motors, from steady state, solid state components to full motion and complex machinery. And then we can understand them not only from a electromagnetic point of view, but how does that electromagnetic performance affect things like the thermal behavior? Do we overheat the system? Where do we generate heat? And what can we do with that? And then also the level is understanding the level of detail we require. Do we need to do a full 3D model, or can we get away with a slightly simpler model that still represents the main physics that we have or that we need to describe that system? Okay, and then from this we can look at when we build up a 3D model, we can really get the detail of how these components work in reality. So we can look at things like skin and proximity effects and other parasitics that might occur from our design. And then we can go about and address them and fix them and hopefully improve our design, to look at increasing power density and reducing the thermal load on our system as well. So to this end, we have a number of different sort of advanced models to help us characterize particularly the materials. And these type of systems are very important to their behavior. So we can look at things like demagnetization, from the thermal performance, maybe it overheats and demagnetizes. We can look at hysteresis modeling of the different materials. We have various core loss models that can be implemented, as well as looking at magnetostriction. So when they actually have the sort of shape change of the material from the EM field, and how does that affect the vibration response of the system. And we can even turn that into a noise, vibration, and harshness analysis, and we can see what is the noise that this model is going to make. That characteristic whine of a electric motor as it speeds up. We can actually then predict that and see whether it is within acceptable levels. And then looking at a bigger system now, at a data center, looking at power distribution within that data center. Again, what level of detail, we kind of have an offering for different levels of detail within that system. So we can either model, for example, the power delivery as maybe just a circuit diagram, or we can look at the actual physical cables and bus bars and that are sort of operating right together, and seeing how they actually operate in real world conditions. And then couple that with some sort of cooling system, and trying to understand, is the cooling sufficient for the heat that's generated within this type of model? Okay, so yeah, have different tools depending on which kind of level we want to look at there. Yeah, nothing's really kind of out of the scope of what we can work with. Then once we've kind of characterized the electromagnetic performance of the component, we can then start considering the thermal behavior. Okay, so we can actually use the electromagnetic solution, the field model that we've generated, and actually translate that into a thermal model. So look at like ohmic losses in the material, for example, and see where the component is most likely to heat up. Okay, so the idea is that we can start then understanding from our design, where is the heat generated and how can I get rid of it? Okay, and in this case, we can look at different scales. So we can go right up to the physical die scale of the actual chips, right up to the PCB level, and then also even to the housing that it's mounted in, and looking at all the ancillary components that go with that. So like your heat sinks, cooling fans, etc. Typically, your thermal loads are due to the operation of the components, like your power loss on the PCB, but they could also be a result of some sort of external condition, like a hot air that's been blown over them from other equipment or just bad cooling design. And so we can bring in the thermal loads from both sort of internal in the component as well as externally, and then try and understand where are we going to have any hotspots? Are they going to be located around any sensitive components? And are we going to cause those components to overheat and work beyond their design temperature? And if so, then how do we go about cooling that better? We can also then consider operational cycles. So whether we are, operating this thing as sort of on-off cycling, when it's working, not working. Is it a day-night cycle where there's hot temperatures and cold temperatures? We can always include that as well into the design, or into the analysis at least. And I think it's very important to also just remember that these kind of electromagnetic thermal simulations are actually a bit of an iterative or coupled approach, in the sense that as materials heat up, their material properties can change, which then affects their electronic performance, which then again changes their temperature. So we do need to consider that or relationship there. So we need to be able to iterate backwards and forwards between our EM model and our thermal model, so that we can, use our updated information, updated thermal field in our electromagnetic model, and then our new material properties can then go back into our thermal model for sort of a better estimate as to what's going on. And that often takes sort of 3 or 4 sort of iterations back and forth to get a more realistic design. In some cases, I've seen the final temperatures be as different as 20% from the original estimates, just because of this sort of iteration and updating of material properties. So it's certainly something to consider when doing the analysis, and we have a number of automatic solutions for that kind of back and forth coupling between different physics. Here's an example for thermal management of a electric vehicle inverter. So this is something where we've actually done the 3D analysis of the component, turned that into a thermal model. And in this case, they even went as far as doing a reduced order model as part of a whole power delivery system for the electric vehicle. So just to kind of highlight here is that it's not just the electromagnetic performance that can be considered in the reduced order model. We can also look at the thermal behavior, because as we go through different parts of the drive cycle, the load on the machine will be different, and that's going to obviously create a different thermal load as well. So then we can track the thermal behavior of that component throughout the drive cycle, and understand what is its sort of realistic operating limits And what happens if the drive cycle changes? Will it still be acceptable? And so often, again, we're talking about the system model just because, again, you get this quite a large improvement in time in the sense of looking at these what-if studies and changing drive cycles, and we can still get a fairly accurate representation of the system behavior by using these reduced order models. Okay, here's another example where we're taking a bit more of a detailed look at a specific component. So this is actually a heat exchanger for cooling of components. In this case, we have fluid flowing through these different channels, extracting heat from the system. And what we've done is actually parameterized the spacing of all the different cooling channels, and then we can do a large-scale parametric study to see what is the optimized spacing of these different cooling channels. Is it better further apart, closer together, or do we need more of them? How can we get the most out of this particular heat exchanger? So this is where we can do large-scale studies, parametric studies, create a response surface, and then we can understand how this specific component works. And obviously, you can see all these little dots represent a particular design point that we've simulated, but there's also various tools to try and minimize the amount of design points that we need to characterize this whole range of parameters that we're studying, so that we're not simulating hundreds of models, we're simulating maybe 10, 20, 30 models instead to mathematically characterize this operation region. Okay, so again, there are tools to try and help us speed up our design, making sure we test all the different possibilities that are out there to find the best one. All right, then when we look at EMI and EMC type problems, this is now obviously as the components get pushed closer and closer, they are going to start interacting with each other. And we do need to start understanding what is their influence from one component to the next. So using this example here of an electric vehicle, we've got a powertrain that needs to meet certain EMC tests, compliance tests, and make sure that the components are not interfering with each other. So to look at a large number of design variations, again, we've gone to a system model where we've characterized each of the individual components of the whole system by their own sort of model, 3D model, but now we've put them into a reduced order model running through a design, a drive cycle, and then we can test how the whole system operates together. Okay, it's not just about one component, but it's about all of them together. And then when we look at in the 3D scheme, we can also then do an EM analysis of this whole model, look at the interference of the different components as they lie next to each other. So for example, we've obviously positioned the battery and the motor far from each other, but we have these large power cables running up and down the vehicle, and how do they interfere with maybe the signal wires, for example. So again, looking at different scales of the model, we can extract different information about the system and get a sense of the actual performance of the system. And this allows us to then also get a lot more confidence in the design, particularly when we have to get to these compliance tests. Do we actually have confidence that the design will work as intended? Okay, here's an example of a certification test for the CISPA 25 standard. For these standards, there are many tests that need to be conducted. This is obviously costs time and money, especially when your product is sitting on the test bench in the middle of the certification test. So the idea is if we can run through all or most of these different scenarios before even leaving the design lab, we can then potentially save a lot of time and money. And in this case of this particular example, we can save particularly up to 50% in both time and cost, time and money associated with these tests. So when we work with packages like HFSS or Q3D, we can actually virtually reconstruct these different test scenarios with all the different components, right down from the test bench to the whole anechoic chamber. And so we can then get quite sort of realistic results that we should see in reality in the actual tests. And we do this because we have an actual library of standard components, which we can then bring into our model to kind of build up this test apparatus. Okay, and so it's all just about getting this one-to-one representation of what we see in the computer, see in real life, and can we then we can then have confidence in what we are measuring and comparing with the simulation. Okay, and here's another example, but at a bit of a smaller scale, where we're looking specifically at EMI and EMC at the PCB level. So with a product like SI Wave, we can look at both the power and signal integrity of the actual individual traces on a PCB. Okay, SI Wave is a solver that's specifically designed for analyzing PCBs. So we can actually bring in the board layout from the ECAD files directly from the designer of the PCB. And then we can start adding details like all the board mounted components and the operating currents and voltages and so on. And because we can bring in that ECAD file, obviously then it's exactly like we've designed it. It's not some approximation that we've guessing here. It's the actual design that we're working with. And then take that design and we can actually predict phenomena like crosstalk between neighboring trace lines fairly easily. We can start creating contour plots, as we can see up here, top center, where we can actually then get visual feedback as to where the problems are occurring. Okay, and then it takes a lot of the guesswork out of, where are the problems coming from. And then if we want to work more in a 3D space, obviously PCB is very planar. Some people talk about it as a 2.5D space because it's essentially layers of a board. The layers are 2D and then you just kind of stack them. But if we want to get into more of a 3D type model, we can then use HFSS to look at the full 3D field values. Okay, and in that case, we can even then parameterize things like the trace dimensions, in order so we can kind of actually do a parametric study, an optimization study on their size and layout, and understand what is their effect on the 3D field from there. Okay. And also sometimes the EMI actually comes from a component that's being placed onto the PCB. In this case, we can actually link both SI Wave and HFSS together. SI Wave to handle the PCB level analysis, HFSS to do the component level, and we can then do the combined simulation and understand the influence of that component onto the PCB. Now we look more at the mechanical side of reliability. So this is where the influence of either thermal or physical shocks come into the PCB and the reliability prediction of that PCB. So, these environmental load or these physical loads could be due to the operation of the components, either, the current draw causing sort of heating of the components, or from external environmental stresses. So, for example, transport of the component to site. We've had an extreme example with a client where the intense vibration was or they experienced intense vibration coming from the launch of their component into space on a rocket. So we can then test these things ahead of time and understand their effect on our component and the reliability of the component. And so the idea is that we can then, with something like what we're highlighting here with Ansys Sherlock, is that we're specifically looking at the PCB board level with the actual components on the board. And so the idea is we can then actually identify specific components and estimate whether those components are going to be failing or not. maybe a component, a particular chip is sitting in a hotspot on the board, and maybe it's running out of its design temperature, and it will then fail because of that. And so we can identify that on a component by component basis. And then obviously the idea with Sherlock is we put our components or our PCBs through our real world physical events that we can actually experience, so we can understand the operational effects, we can understand transport. Maybe there's some other, challenges that come along, like heavy vibration or something like that, or dropping the component for installing it. How does that affect our reliability? And also the idea is then to try and not only speed up design, but also make sure that we meet our compliance standards. Okay, so make sure that we can put the board virtually through all of our different compliance tests, and make sure that it will last and pass the requirements. Okay, and just like we saw before, Sherlock can import most ECAD formats, so we can then work with that exact board layout as it's been designed, and so we get a very accurate picture of what's going on in the board. So Sherlock can account for the fact that there's maybe more copper in one area of the board than the other, and how does that affect the thermal behavior or the shock behavior or something like that. And then we can also go down to the level, as we can see in this image here. We can not only consider the components, but also their leads and how they attach to the boards. Are the leads going to fail? Or the solder going to fail, the solder joints? What part of the component is going to be our weak spot, and what needs more attention to make sure it lasts? Okay, and then maybe something else just to add from here. So Sherlock has quite an extensive parts library as well. So all these components that we place on the board, they will be detected from the ECAD model itself, but we can then also go and select components from this massive library. I think it's like 10,000 parts last time I heard. And these are all manufacturers' parts as well. So we don't have to go and dig through all the data sheets to go find that information. It's all there available to us. And then when we do our analysis, it's all designed to be within Sherlock. So Sherlock is designed for, sort of the PCB engineer. It's not, it doesn't require an FEA expert or some sort of simulation expert to go and work on this. The idea is that we can do these quick analyses within the Sherlock environment, and it's all done in a way that we would understand as a PCB engineer. Okay, so you don't need to know necessarily what an FEA mesh is. That's all handled by Sherlock in the background, and all we can do is get the results for our reliability analysis. However, if we do want to add some more complexity to our model, maybe we need to consider the actual structure around our PCB. Maybe there's specific mounting points that we need to consider. All of that can be then added within, or in that case, we do need to move over to our FEA solver called Ansys Mechanical, where we can then start adding all these extra components and do a much more rigorous mechanical test. Okay, so all the usual thermal, vibration, all of that, but now we can include a lot more detail than just the PCB level. Okay. All right, and then from a thermal side, we also have a few options available to us. So Sherlock does also include a thermal model, so it can predict the component lifetime and failures due to thermal cycling over the life of the product. One can also then generate a realistic heat map that basically we can use to get more accuracy for specific components. So maybe one component is located in a hotspot, and that component is more likely to fail than the same component in a colder area, for example. So that can all be done within Sherlock. For larger scale thermal analysis, we also have a product called IcePack. So this is a sort of more traditional CFD-based solver. It's actually based on our flagship solver called Ansys Fluent. And what we've done is repackage the solver for electronic thermal engineers. So the idea is that there's a lot of tools that are there to help you deal with more common components, things like heat sinks and fans, so that there's kind of only minimal input in terms of the simulation setup, things like your mesh settings and solver settings and that. A lot of that is taken care of in the background, so that we can then focus on just the performance of the electronics instead of all those other settings. And then with these tools, we can then put the PCB through its paces under the real-world operating conditions and make sure that we can keep the board cool enough to have the components operating in their intended or designed operational ranges, and hopefully then prevent any early failures due to thermal fatigue. And again, we can look at the design from all levels, right from the small chip design to the actual enclosed PCB in the housing with all its other components around it. Okay, and then one of the other areas that we might need to consider, which is probably becoming more and more prevalent, is that of embedded software and control. Okay, it's not just looking at the physical components, but how do we control them, and how does that influence their operation, and particularly how does that affect their safety? Okay, so as we start, running these systems in more sort of higher stress environments, we also need to consider the safety ramifications of what if a component fails, or if we're operating even as normally, is it going to operate as it is intended? Okay, so the idea is that we test the integration of the components with their control software as well. Okay, and this is what we have, a product called Ansys Scade, which has the ability to generate qualified code, which is actually based on the system architecture of our model, of our system. And this code is generated automatically. And it's actually, because it's generated automatically, it's certified for various standards. So just the way that it's structured and it's created, it adheres to all these standards and will then be straight, or it's actually automatically verified or certified for those different standards. Okay, and so this will definitely reduce the need for all the verification and validation testing that has to be done with this control software, because we can automate the testing for all the different performance parameters and identify any potential bugs that could cause a system failure. The failure could come either from a complete crash, or it could just be a failure because the system doesn't actually operate as it's designed to. Okay, so we can, the idea is that this automatically generated code obviously speeds up the development time and coding time. We don't have to pay a coder to sit for weeks and do it. We can just generate it automatically. And we know that because it's automatically generated, it's fully traceable, and Scade will do full reporting on the structure of the code, so that we can then have complete confidence in that product, and make sure that we have that confidence in all these safety critical applications. Okay, so in this example that we are illustrating here, we have a powertrain for a sort of electric vehicle, for example, and we have a full system model with our Scade software implemented in it. And the idea is that we can then test the system virtually for, say, a real-world failure. So in this case, a sensor wire breaks. How does the system behave? We can track the signal or the behavior through the system, and see if the system then interprets it correctly and behaves in a safe manner. Okay, so in this case here, we actually using Medini Analyze, which is another Ansys product. to define the safety requirements for this particular system. So this could be a safety requirement that comes from either yourself or from your client. We define this as a goal and devise our fault tree analysis and all of our safety requirements around that. And that can be integrated then with SCADE to have a much better sort of operational requirements for our code. And then when we have the same breakage, we now find that there is a safe shutdown of the system. Okay, so that way we can, before we even go and test this, build the prototype and run it. We're not going to have this vehicle break because it crashes. We're going to see that it will have a safe shutdown and prevent any harm from happening. So the idea with SCADE is that we build up our system model. We call this a model-based system architecture. And then we translate that model, that system model, into the actual computer code as required to operate the system. Okay, so we can start with simple control algorithms in Simplora. So these are the system models we've been seeing in the previous slides. But then we can translate that into a system architecture model here designed in SysML language, where we actually describe the control logic of the system and how it interacts with the different components. And then through SCADE, we can generate that code from this architecture model. So it will interpret our intention behind our design and how the logic information flows, and it will generate the control code for us. So here, again, another sort of drivetrain example where we've got our power source coming from wherever it comes from, battery or something like that, through our power electronics into even our motor. In this case, they've even created a reduced order model of our synchronous motor, and then connected it also to some sort of load. So this can be a real-life drive cycle or load, driving up a hill or something like that, or braking. And so we can even simulate those kind of loads on the system. And then we've connected that to the control software. Okay, so the embedded control software through our components. We have our input, which is maybe our driver's inputs into the controls, and we can see how that then controls the rest of the system. So we can test this model under different input signals and see if the control software actually behaves as intended. Does it control the motor as we expect? Or does something happen that is actually unsafe, and then we need to go and correct that? Okay, so this is kind of tying off the different areas or disciplines within power electronics that we have solutions for. So right from the physical components themselves to looking at the larger scale system models to also then the control software for those different components. Okay, so Ansys has a number of different options depending on your needs. So if you have any particular challenges, you're welcome to reach out to us and just find out what solution would work best for you. All right, that's it for my talk. Are there any questions?